Hi everyone, welcome to the post-contest discussion of the Codeforces Round 989. This is TLE Eliminators and I am Abhinav. So let's get started with our first problem. Okay, so in the first problem, we are given some story. Let's ignore that. The riddle involves two sacred numbers A and B. To unlock the vault, the challenger must determine the smallest key number M that satisfies two conditions. M must be greater than or equal to at least one of A or B. The remainder when M is divided by A must be equal to the remainder when M is divided by B. Okay, so we need to determine the smallest number m which satisfies these two conditions. Okay, and we are given two integers a and b. Okay, so let's say we are given 4 and 6. What we need to do? Okay, so like we are given two integers a and b. We need to determine the minimum m so that it satisfies two conditions. What are the conditions? The first condition is m must be greater than or equal to at least one of A or B. That is, m should be greater than equal to A or m should be greater than equal to B. Either of the two it can satisfy. And the second is the remainder when m is divided by A must be equal to the remainder when m divided by B. That is, the remainder when m divided by A, which can be said as m mod A, this should be equal to remainder when m is divided by b. Okay, so we need to find the minimum m which satisfies these two conditions. Okay, so if you look at the conditions carefully, okay, let's say if you look at the test cases, let's say a was when 4 and 6. A was 4 and B was 6. Okay, so what m would you choose? Okay, if you choose some very small m, let's say m equal to 1 or 2 or something like that, it won't satisfy the first condition that m should be greater than either 4 or 6. Okay, so basically the first condition can be rewritten as m should be greater than the minimum of A or B. Okay, both mean the same. M should be greater than either of the two or greater than the minimum. So if minimum of 4 and 6 is 4, so m should not be less than 4, that's for sure. So the first thing is m should be greater than equal to 4, that we can understand from the first condition. Now, what we can understand from the second condition? Now, the second condition states that the remainder when m divided by A should be equal to the remainder when m divided by B. Okay, so let's say we take m equal to 4. Then 4 mod 4 would give us 0, but 6 mod 4 would give us 2. Okay, so these are not equal. Or we can take m equal to 5. Okay, then 5 mod 4 would give us 1, but 5 mod 6 would give us 5. Again, they are unequal. At m equal to 6 also, we would get like mod 4, we would get 2, mod 6, we would get 0. They would be unequal. Okay, so if you observe carefully, you can try m equal to 7, 8, 9. Likewise, when you would reach m equal to 12, then you would say that 12 mod 4 is 0 and 12 mod 6 is also 0. Then both of them are equal. It satisfies the condition. Now, how can we just, okay, one way is I think looking at the constraints, you can probably do a brute force, but the brute force may go up till A into B. So that may give 1 is 6 into 100 test cases. It would be a tight case. So you may do the brute force thing also, that may also pass. But if you just observe a little bit more carefully, you will get a way easier and better answer, that which is the minimum m that would satisfy it is if you have some like 4 and 6, whatever m you take in between, like 5, 6, like in between 4 and 6, whatever m you take, they would, for 4, it would give some remainder. For 6, it would be equal to like the x. So when x is in between A and B, then I would say, then x mod B is going to give me x only, but x mod A is going to give me something less than x. So they won't be unequal. Now, when I go above B, okay, at x equal to B, it would give me 0. But uh, if A is if A is divisible by B, then we would get a 0 for A also. So which is the first number where both of them would be equal would be actually the LCM of A and B, because at that point we would get both A and B as 0. So like 4 and 6, their LCM was 12. So there at 12, we would get the remainder with 4 and 6 both as 0. But whenever you are below the LCM, okay, at any point, if you are telling that they both of the remainders of 4 and 6 is equal, let's suppose I say that LCM is not my answer. One thing you can understand, that LCM can surely be my answer. Both would be 0. But if I take any x less than the LCM of A and B, okay, let's say I want to prove that is LCM the smallest one, or can we have something less than that? So if I take any x less than the LCM of A and B, and I'm telling that it satisfies the condition of x mod A is equal to x mod B, that means remainder with A and B, they are equal. So if I go whatever, let's say the remainder is R, okay, let's say x mod A is equal to x mod B, and that remainder is R. So if I do x minus R, okay, that should be a divisible by A. Okay, so that should be a multiple of A, and x minus B, that should also be divisible by A. Okay, what does remainder mean? If dividing by A gives me a remainder R, that means x minus R was a multiple of A, and x minus B was a multiple of B. So that means, sorry, x minus R only. So that means x minus R was a multiple of both A and B. So x minus R should have been the LCM of A and B. But we know that x is less than LCM of A and B. So definitely x minus R is not the LCM. So this way, like, we can prove that LCM of A and B would be the smallest value at which we can say that uh, it would satisfy this condition of both M mod A is equal to M mod B. Okay. Because if we are assuming anything less than LCM is possible, then from here we can prove if X was possible, then X minus R was also possible. So X minus R should have been the LCM, but we know LCM is the smallest common multiple. There is no multiple which is common among them less than LCM. Okay, so from this, I hope you understood the proof also why LCM of A and B would be our answer. So we can say we can just directly print the LCM of A and B as our answer. Okay, so the code would be very simple. You just So the code would be very simple. You just take the input A and B and print the LCM of A and B. This LCM function computes the LCM in log of either A or B, log of whatever maximum min of A and B. So you can say that overall time complexity that we would get is the time to compute LCM. That would be order of log of max A and B, or okay, that's the time complexity to compute LCM. I hope this problem is clear to you. Okay, someone said you loop too. I think the brute force would also get accepted if the time is not, it is 1 second. So if you are doing looping till 1e6 and you have 100 test cases, overall it's 1e8. So it may in very edge case pass. So I think that would be okay. Okay. So I think this problem is fine to you. We can move to the next problem. I hope this was understood why LCM of A and B would be our answer. Okay, so let's move to the next problem now. So in the next problem, again, let's ignore the story and move to the actual question. We are given a binary string of length n, where each 0 means a weak spot and each 1 means a strong one. Rostam's goal is to make sure that no interval of m consecutive spots is entirely weak. Okay, so we need to make sure that there are nowhere we have m consecutive zeros. Okay. Luckily, Rostam has a special ability called Timar, inherited from his mother at birth. With Timar, he can select any segment of length k and instantly strengthen all of it. Basically, he can select a segment of length k and change all the values to 1 in that segment. Challenge is to figure out the minimum number of times Rostam needs to use Timar to keep Rakhsh moving, ensuring there are no consecutive entirely weak spots in length m. Okay, so basically we are given a string, and in that we are given that that string should not have any consecutive m zeros. Okay, so we need to make sure that the string should not have m consecutive zeros. To make sure we can perform some operations. In every operation, we can select a k. Okay, so we are given n, m, and k, so we can select a k. Okay, let's take it there only. So what the problem states is we are given n, m, k, and a string. Okay, so we are given a binary string. Okay, let's say some binary string we have. Okay, and then what we need to make sure is in this binary string, there should be no occurrence of m consecutive zeros. Okay, let's say m is 2. That means there should not be two consecutive zeros anywhere in the string. Here we can see there are two consecutive zeros. There are even three consecutive zeros. Okay, so this two consecutive, two consecutive, two consecutive, there are many occurrences of it. So we need to do some operations on this string so that it doesn't have m consecutive zeros remaining in this. Now the operations we can do is we can select a segment of length k. Let's say our k was 3. So what we can do, we can select a segment of length 3 and change all of them to 1. Okay, that's what we can do in one operation. Okay, so we can do this operation multiple times and we just need to find the minimum number of operations to make sure this string doesn't have m consecutive zeros. That's what our problem is. Okay, so if you look at this test case, here, if we are given ms2, ks3, and this string is given to us, then what would be the answer? What we can do is, okay, there is only 1 0 here, so no need to worry about that. We need to make sure there are no two consecutive zeros. Here you can see there are three consecutive zeros, okay, which is much greater than 2. So we need to change some of them in order to avoid the situation of having uh, more than two consecutive zeros. So what we can do, here we can we have k equal to 3, so we can perform an operation here. Okay, let's say we performed an operation here and changed all of them to 1. Okay, so now we have this 1 1 1. Now here we have two consecutive zeros. Okay, so again we can perform some operation of take a segment of length k and make them 1. So let's take this segment of length k. Okay, so we can take this segment of length k. This one is this one would remain 1 and these zeros would change to 1. Okay, now the string that we have, there are no consecutive two zeros present in the string. So we can say this is a valid string and the number of operations required was, this was one operation, this was two operations. So 2 would be the minimum operations required to convert this. Okay, so this was just one test case. Now, how do we optimally do this? Okay, so if you observe carefully or just think a little greedily, so what we need to do is we need to minimize the number of operations. Okay, so what we have a binary string. Okay, so there is some binary string, there would be some zeros, then some ones, okay, then some zeros, ones, zeros. Likewise, it would be there. Okay, let's say we have any random binary string and we are given a m and a k. Now, how can we solve this problem is we need to make sure there is no m consecutive zeros. Okay, so we would only look at the zeros. Okay, so we would look at those segments where we have consecutive zeros. Okay, let's say initially here we have many consecutive zeros and the number of consecutive zeros are greater than equal to m. That means we need to do at least some operations here. Okay, otherwise uh, it won't. So we need to do at least one operation here. Okay, now how would we optimally do the operations? Let's say here we had 1, so here the number of zeros here was less than m. So we don't need to do any operation here. There was no problem. So even if the number of zeros is equal to m minus 1, there is no problem. Whenever the number of zeros reaches equal to m, after that we have problem. Okay, that's the thing. Now we need to do it in minimum operation. So whenever we do an operation, we can just change k consecutive zeros into 1. So that would just solve some issue. But how do we minimize the number of operations is what we can do is greedily until I have m minus 1 number of zeros, I don't need to worry. The let's say at the ith place, I got a 0 and we have now m consecutive zeros. Now what I would do, among those m zeros, at least one of them should be changed. Okay, so in this string, if at the ith position, I got that now we have m consecutive zeros, then among those m zeros, at least one of them should be changed, that's for sure. Okay, now where would we apply our operation? Okay, if we apply our operation here, if we start our segment of length k from here, okay, then we are changing all of these zeros. Or if we start our, if we apply operations from here, then still if this 0 is changed to 1, this segment of m minus 1 zeros is fine, there is no problem. But if we apply an operation here, we are in the forward direction, maybe also again we can have some zeros. So if we are applying the operation here, then we are also maximizing our chances of maybe in a single operation, maybe there was some more after this, some more consecutive zeros were there. So let's say m was 5 and k was, let's say, 7. So here we had 1 2 3 4 5 consecutive zeros, and here again we had 5 consecutive zeros. So if you apply an operation starting from here and change these 7 places, okay, so if you change these 7 places into 1, we still like, let's say we have one more zero, okay, or let's say k is 6 only. Okay. Okay, so if we apply an operation from here and change all of them, these ones would be, these zeros would be converted to a 1, but these 5 zeros would still remain. We would have to apply another operation here in order to change it. But if we start our operation from here and apply an operation on these 6 zeros, let's say, these 6 places, let's say, so all of them would change to 1, and then here we have only 1 0, and here we have 4 zeros. So nowhere we have 5 consecutive zeros. So in one operation we would be able to do, okay, so if we apply an operation here, then in one operation only we are able to do our job. But if we had applied an operation here, then we would have to apply another operation. Okay, if we apply operation here, we would have to apply another operation there in order to do that. So like greedily, you can understand it's always beneficial to, when would you apply an operation? When you are at this place that you have to definitely apply because you have got m consecutive zeros. And then you would apply the operation starting from the mth zero only, because you can have m minus 1 zeros before, no problem, that is fine. But if you apply from here, then maybe in the forward direction also you have some zeros, those are also converted to 1. So that would be beneficial going forward. So with this greedy approach, you can just minimize the number of operations to do it. So what basically we would do, we would start, okay, whatever binary string that we have. Okay, we would start from the first character. If it is 1, then okay, move forward. Whenever we get a 0, we would keep the count of consecutive zeros. Okay, we let's say in C we keep the count of consecutive zeros. So if we keep the count of consecutive zeros, whenever we get a 0, we do a +1, a 0, again we do a +1. When we get a 1, we would reset our C to 0, because now those zeros are okay, they were fine, they didn't reach our M. Now we have a 1, our consecutive zeros is again 0. Now whenever we get a 0, it's one consecutive 0. Okay, before we got a 1, so it's not consecutive. So whenever we get a 1, reset C to 0, and whenever you get a 0, do a C++. This way, we can keep the count of consecutive zeros. Whenever the count of consecutive zeros reaches m, okay, let's say here the count of consecutive zeros reaches m, then we would apply an operation starting from that index up to length k times we would apply the operation, next k values would be changed to 1. And then start checking after that, because those 0 are already changed to 1. Start checking after that, reset your C to 0. Okay, so like in the code, I'll explain in more detail what I have done. So we take the input n, mk, and the string s, and then I run a loop starting from 0 to n. I would iterate. I maintain a C variable which will store the number of consecutive zeros. Okay, so whenever we get the string value as 0, then we would do C++, and else if we get a 1, we would reset C to 0. This way we are keeping the count of consecutive zeros. Okay, and whenever these consecutive count reaches m, then what we do, we would do an answer plus plus. Yes, we are applying an operation. And what we would do is we'll apply an operation. Okay, let's say at this ith index. At this ith index, I say that I have m consecutive zeros. Then from this ith index up till I plus k minus 1th index, all of them would change to 1. Okay, because these k consecutive indices would be in one operation, they would be changed to 1. So we can just instead of changing them, we can just ignore them and move to the next index for our checking. Okay, so like changing the string was not required, only updating the answer was required. So you can change the string also, there is no problem. In my code, what I did is just I moved to I plus k directly. From I did plus equal to k minus 1, because next time when I go to the for loop, I would again do an I plus plus. So basically I'm doing I plus equal to k here, because after this it would go to the updation part and it would become I plus k. So basically when at I, if we apply an operation, then from I plus k, we again need to check till I plus k minus 1, they are all changed to 1. Okay, so that's what I just did. I reset my C to 0, I plus equal to k minus 1 whenever I reach M. So I hope this greedy approach was clear to you. Finally, I just pinned the answer. I followed the same logic as being discussed, but I don't know where I'm missing an implementation. Uh, okay, maybe at the end you can send your code, then I can look where it went wrong. But yeah, the implementation would improve by practice only. Okay, the more problems you solve, that way the implementation improves. Okay, that's what I can suggest there. Any more doubts in this problem? Is this approach clear to you? Okay, so I think if you look at the time complexity of this problem, what it would be, we are taking this string of size n as input. Okay, after that we are running a loop n times, and here this is an if condition and if condition. So all of these are constant time operations. So this loop is taking n time. So that would only be our time complexity and linear time of order of n. That would be well accepted with the given constraints of n up till 2 into 10 to the power 5. So I hope this problem is clear to you. We can move to the next problem now. Okay, sorry. My screen is visible, right? There was just a small, I got disconnected. My screen is visible and audio is clear, right? We'll move to the next problem C now. Okay. Okay, so let's move to the problem C. So here we have, okay, just a second. Okay. So here we are given that, okay, okay, no, there is something in the story. The maze is a rectangular grid of size n cross m. Each cell in the maze points in a specific direction, up, down, right, left, or right. The witch has enchanted Rostam so that whenever he is in a cell, he will move to the next cell in the direction indicated by the cell. Okay, so if Rostam eventually exits the maze, he will be free from winch, whatever. However, if he remains trapped, he will never escape. Okay, so basically what you need to do is your task is to maximize the number of starting cells which Rustam is trapped in. So basically you are given some grid, okay, where what does this grid represents? That if you are at some point, let's say this, okay, so what does this grid represents? If you are at some any cell in the grid and the arrow is pointing to the right, that means after that you would move to the cell to the right. Okay, then again arrow is pointing to right, so you would move to the cell to the right. Again, it is pointing down, so you would move down. It's right, you would move here, you would move here. Now it's pointing up, again, you would move up here. So if you look at this maze, you would keep on moving inside it, okay, in a cycle, in a loop. Okay, so in this maze, you can say that when you start from this point, you get trapped in the maze. You are never able to come out. Now, if you look at here, if you start at this point, you would move up and come out of the maze. Once you come out, you are freed. Okay. If you start from this point, then you would move down. Okay. Then you would move to the left. Okay. Then again, you would move to the right, to the left, to the right. So you got trapped here. Okay. So you can say that if you start from this point, you get trapped. If you start from this point, you don't get trapped. So you need to just minimize the number of starting points, like maximize the number of starting points, maximum number of starting points from where you get trapped. Okay, here if you see from this, and this, from these 5 cells, if you start, you would get trapped. But for the remaining cells, if you start from this point, you are free. If you start from this point, you are free. If you start from this point, you move here and then you come out, you are free. If you start from this point, you move here, you come out, you are free. So in any grid, you can say that the number of starting points from where you get trapped was 1, 2, 3, 4, 5. Now, you are given as an input some grid, but some of the cells are marked with question mark. Okay. This question mark represents that you can fill up that cell with anything of your choice, either up, down, left, right. Okay. So up, down, U, D, L, R, they just represents a down arrow, up represents up arrow, same way left, right. Okay, so you are given up, down, left, right, or question mark. So if a cell is question mark, you can replace that question mark with either up, down, left, or right. Now you need to make such replacements so that finally in your grid, the number of points from where the number of starting points from where you get trapped is maximized. Okay, so you need to make such replacements of those question marks. Okay. So if you look at the constraints, what you are given is N and M are up to 1000 and their product does not exceed 10 to the power 6 for all test cases. So you need to find an algorithm in something of order of N into M, or maybe some log factor can come, but you cannot go N square M or Mn square, anything in square. So you need to find an N into M. So I hope the problem is clear to you. So for the first test case, here there was just one question mark. And if you look at this first test case, okay, let's look at it here. So if you look at this first test case, what grade it represents is something like this. Okay, this up, it means an up arrow, up arrow, up arrow. This is a left arrow. This is right arrow. This is a question mark. This is down arrow, down arrow, down arrow. Okay, this is what we are given in our question. You can replace this question mark with anything. So if you look, if you are here, you get freed. If you are here, you get freed. If you are here, you get freed. Here, you get freed. Here, here, here. All these points, you would get freed. So you can replace this question mark with any arrow. Let's say you replace it with up arrow, then you would go here and get freed. If you replace with right arrow, go here, get freed. Down arrow also, go here and get freed. Left also, go here and get freed. So whatever you replace this question mark, if you start from here, you get freed. So basically from all the 9 points, you get freed. So there is no point from where you get trapped. So your answer would be 0 in this case. Okay, so your answer was 0. So I hope it is clear. Now, when you have all the question marks, you can make it 6. How? Let's say you are given the test case where all of them are question marks. Okay, it was a 2 cross 3 grid. So what you can do is how to make all starting points as trapping. Okay, one simple thing you can do is have a down and up, down and up, down and up. Okay, whenever like from the this only you can observe from here only. When you have a right and left, okay, something like that. When two cells are pointing towards each other, so if you start from there, you always get trapped. If you start from here, you always get trapped. So whenever you have two consecutive question marks, you can always make them to trap each other. Okay. So that way you are maximizing the number of positions you get trapped. So six would be your answer for the second test case. Okay. So I hope the problem is completely clear and some initial intuitions also you would have got what you can do. So now how can we solve this problem basically? So if you are given some random maze and there are some question marks, okay, let's ignore the question marks for now. Let's understand if you are just given a maze, okay, if you are given a simple maze without any question marks, then how can you find the number of positions where you get trapped? Okay, let's say in an n cross m maze, you need to find the number of positions where you get trapped. So how do you do that? Okay, so here like you would have some left arrows, up arrows, right arrows, or something like that. Some maze would be given to you. Now, if you like analyze what we can do is for the corner points. Okay, the first observation would be for the corner points. Inside points, we don't know. The initial one thing would be sure if I'm at some corner like this and you are going right, then if I start from this point, then definitely I would get freed in one step only. And if I'm at some corner point like this and I go out. So for all those points in the exterior, like the boundary of your grid, for all the points in the boundary of your grid, you know, those points which are pointing outside the grid, from that point you would get freed. So value of that would be like 0, you can say. But for those points, let's say this arrow, where you move towards here. Now, for this case, you don't know. Maybe here, if you move here, then you get freed. Maybe if the arrow was instead of here, let's say the arrow was down, and then here the arrow was right and it was left, something like this. So if you start from here, it is not taking you out, it is taking you somewhere else. Then it would depend whether this position is a position which would get you freed or trapped. Okay, now if you look at this position, here you go to this position. So it would depend whether this position get you freed or trapped. But from this position, you can see that you are in a loop. So these positions you can say get you trapped. Okay, and it's like maybe you may be feeling that the only possibility for getting trapped is when you have something to like this, but that's also not the case. You may have something like this and like this, a circle type of thing forming. In that case also you may get trapped. So for the trapping case, it is not completely sure that if you start from here, you would get trapped or not. That would depend on the next state. Its position would depend on the next state, and we come back in a cycle, then we can say that we get trapped. Okay, so that is a little tricky, but the positions of not getting trapped, that are more easier to compute here if you analyze closely. So here we can say that in this, you would say that here, whenever you start from the boundaries, from the boundary, when you have something going out, you say that, yes, this is a position which doesn't get trapped. You have something going out, this is the position which doesn't get trapped. Now, uh, first for the boundary cases you have analyzed. Now, let's see all the positions adjacent to them from where you are getting freed. Okay, so here you saw that this position gets you freed, this gets you freed. Let me just make it something. Okay, so let's say you have something like that. Now, you can see from this position you get freed, from this position you get freed. Here also you get freed. Here you can't say, here you can't say, here you can't say, here you can't say. Here also you can't say, here you get freed. So I'd mark that this position you get freed. Here also you can't say. Here you can't say, here you can't say. So initially I went to every boundaries and I said that these four positions are definitely the positions from where we get freed. Now, what are the other positions from where we get freed? So all the other positions that we get freed, something would be adjacent to this only. Okay, so if you look at the position adjacent to this, okay, all those adjacent blocks which are taking me here, from there also I would get freed. Okay, so if you look at the adjacent blocks of this, if you look at this block, if I start from here, I would move to this block, and I know after moving to this block, I get freed. So I can say from here that this is also the block which would get me freed. And if you look at the block just this side, so this block is also taking me here. So I can also say that this is the block which gets me freed. Okay. If you look at the block below it, now this is taking me somewhere else. So for this again, I am not sure. I'm uncertain whether it would get me freed. But for these two blocks, I got sure that yes, they would get me freed because they are taking me to a block which is getting me freed. Again, if I look at the adjacent elements of this block, okay, this gets me freed. That was derived from there. From here, if you look the below it, it is already getting freed, so no problem. So no more checking. Now, if you check this, the element just down. Now this does take me somewhere else, so I am not certain. This take me somewhere else, I am not certain. If you look at this, okay, so just above it, this take me somewhere else, I am not certain. This take me somewhere else, I am not certain. So so you can understand from here that what we are doing, we are running something like a BFS, that we start with some initial source nodes. If you just look at the boundary, we would get some initial nodes, and then we are just moving adjacent to that. Okay, just we are checking adjacent to that. Whenever we get something from where, which is pointing towards that node only, that I can say that it gets freed. Now I can check like recursively or whatever. In BFS, I would check, I can check to the next adjacent. Now, in the initially, I got these four initially I got, which gets me freed. Now, when I analyze the adjacent node to them, I got these two also, which gets me freed. Now, I analyze the nodes adjacent to these two. So adjacent to this, I have this, which again takes me somewhere else, so I'm not certain. And adjacent to this, I have this, which takes me somewhere else, so I'm not certain. So again, so if we have analyzed all of them, okay, so these would be the only nodes which get me freed. All the remaining nodes are going to get me trapped, that I can say. Why? Because let's say there was some other node which is getting me freed, then if this node was getting me free, there would be a path to go outside. So if there was a path to go outside, then whenever we started from the boundary condition in the BFS, we would have reached here by going to the adjacent nodes. But if there is some node where we are not able to traverse in our BFS, then we can say that from this node we are always going to get trapped. There is no way to go out from this node. So I hope now it would be a bit clear that if we don't have a question mark, okay, for the case when we don't have a question mark, how do we compute? So what we do is, when we don't have a question mark in a grid, we start from the boundaries. Okay, from the boundaries, whichever for whichever nodes, like for whichever grids we are sure that it would take me out, we would put them as the initial source nodes into our queue. Okay, and then we would move adjacent to them in our BFS ordering. Whichever takes me towards that, they would again be put in my queue. Okay, that way we would expand our queue, and when we finally come out of the BFS, all those nodes which are visited, we can say that they are the nodes from where we get freed. And all those nodes which are not visited, from that we can say that we get trapped. Okay. So I hope this initial observation and this algorithm is clear to you. Now, when we have question marks, so what we do? Okay, so this was just to calculate for a given grid. Now, let's say there are some question marks. What we need to do is, we need to replace these question marks so that we need to try to make them as the grid which gets me trapped. Okay. we need to make it the grid which gets me trapped. So we would try that this question mark doesn't take me to like this question mark doesn't is not included in my BFS. That's what we would try. So whenever we reach a question mark, okay, so when we know reach an left, right, up, down arrow, then in my BFS traversal I know that by looking at its arrow we can analyze whether we want to insert it into our queue or not insert it. That would depend, like if you are checking this from this, so if its arrow is just opposite, that from where I'm coming, if it is pointing there only, then I would include it. Now for question mark, I don't know. So if you look, what can we do for a question mark is, let's say I'm coming to this question mark from, let's say this grid was, okay, let's say this was above. So when we reached here, we would go to its adjacent and we would say that this is also included as a grid which gets me freed. Now from here, we would check the question mark. So if this question mark was an up arrow, then I'm going there. So I would say that this would get me freed. But what we want that it should not get me freed as far as possible. If it is impossible that replacing this question mark with anything gets me freed, then okay, no problem. But if there is any possibility of replacing this question mark with anything that doesn't get me freed, then we would replace it with that. So when we are at a question mark, we would only take it when for this question mark, all the adjacent elements get me freed. Okay. If there is any one adjacent element which doesn't get me freed, okay, let's say this is an adjacent element which doesn't get me freed, then I'll point this question mark towards that so that I don't get freed. So this question mark would be included only if for all the four sides, they get me freed. So while running the BFS, we are not entirely sure that which one would get me free or not. Okay, at the end only we are sure. But what is the thing that we are sure while running? For those which we have visited, that are sure that they get me freed. For those which are unvisited, for them we are not sure. Okay, so what we would do is whenever we have a question mark adjacent to us, okay, and for that question mark, if we look at the adjacent values, if those adjacent values, if all of them have already been visited, then only I would replace it with visited. I would visit it. But if there is any value which is uncertain, then I'll assume that this value was not visited. If it get visited in future, then again through that I would reach the question mark. So at that time, that question mark would be included in my queue. So what I would do is whenever I reach a question mark, I would check all the adjacent elements of that question mark. If all the adjacent elements are already visited, then only I would visit that question mark and mark it true. If there is any one adjacent element which is not visited as of now, then I would say that I would not include this question mark. Okay, I would wait either that remaining also gets visited, then through that when I reach the question mark, that time I would visit it. And if it never gets visited, then I'll point it here and say, for this, I get trapped. Okay. So that's the small change that I would make to my initial BFS algorithm when question marks is included to accommodate the question mark is whenever we have a question mark to the adjacent, check all the four adjacent to the question mark. If there is any one value which is not visited, then don't include the question mark. Otherwise, include the question mark. I hope it is clear. Like if it was not clear, why, then one more way to describe it is, let's say let's say you, okay, what would be the case when you have two question marks adjacent to you? Okay, when you have two question mark adjacent to you, always you can make this arrow point here, this arrow point here, and make both of them as getting trapped. Okay, so for any adjacent question marks, okay, for this question mark, whichever is adjacent to that, all of them would be not trapped. Okay, when would be the case when this question marks get me freed? Would be the only case where I have a question mark and all the grids adjacent to them get me freed. Okay, somewhere this gets me freed, this gets me freed. Let's say this gets me freed. Okay, and this gets me freed. Okay, so if a question mark is at a place where all the four adjacent of it gets freed, then only this question mark would be replaced by getting freed. Otherwise, it would be replaced by getting trapped. Even if it has any one from where we get trapped, then point it there. Or if we have anything to it which is a question mark itself, then point there. That is also valid. So if you have anything which is a question mark or which doesn't get me trapped, then it would not get me trapped. Only case when it would get me trapped is when all the four adjacent get me trapped. Okay, I hope now it is clear to you. If there is any confusion, now you can ask. Yeah, it's multi-source BFS only. Okay. And somebody used DFS. I don't know if because we need to start from some source and then go. So a multi-source BFS was more intuitive here. If you, yeah, with DFS also you can actually do like we only just need to visit. So if you like do a multi-source DFS type also, that also would be fine. If you start with some values and just visit all its adjacent in DFS order also, because the ordering doesn't matter. We only need to check whether we visit or not. Okay, so a DFS would also be fine here. Can we do it like basic DP? Okay, like DP was not the solution here because you can apply DP only when you don't have anything cyclic kind of thing. Here you can have some, here if you, for a IJ, okay, like if you're writing a DP, then you would say that for DP IJ, I would check all its adjacent elements. Okay, if any of them is getting me like not the adjacent, if I'm writing DPIJ, if it is pointing upward, then I would say whatever is the DP value of this, that would be the DP value of this. Okay, but if this is pointing upward, this is pointing here, this is pointing here, this is pointing here, then like you can imagine if you are running a DP, you would in the recursion, you started from here, you say that it is equal to dp of this, you say this is equal to dp of this, it is equal to dp of this, and it is equal to dp of this, which is also not computed. So you would move in a cycle and your recursion would never end. So for dp, it's always needed that when you are writing a transition for a state ij which is not computed, the transition for the DP stage that you are using for the transition, they should be computed. Okay, so there should be an order through which you move and you can compute all of them. But here, like in DP, there is no order, but the order to compute is if you start with some different sources and run a BFS kind of thing. Okay, so I think that is clear to you. Like in a grid type problem where there can be cycles, we use the concept of BFS and DFS, the graph concept instead of DP. Okay, if it was like there is movement of only right and down allowed, okay, then there was no cycle possible, then you can use a DP there. Okay, so I think the approach is clear to everyone. So okay, we can move to the code now. Okay, so what I'm doing here is I just take the input, a vector of string, so of n cross m. Then, okay, one edge case which was very like you needed to observe here was, and that's why I was getting some wrong answers also on this, is like if you write a simple BFS on some grid. Okay, what I did is for the initial sources, I moved to all the sides, all the boundaries. And if you have a question mark in a boundary, what do you do? When you have a question mark in the boundary, you can say that you won't replace it with anything going out. You would replace it with something going inside the grid only. So you won't put it initially in your queue. You would only push those values which are certain. But if you have a grid of only one element and that is a question mark, okay, so in this case, if you don't put it in the queue and just then your BFS would end and you would say that there is no value with, so all the values can be trapped, you would say, then you are wrong there, that if you have a n equal to 1 and m equal to 1 for this case, and that is just a question mark, then whatever you do, you would get freed. Okay, either it would be up, down, left, or right. Okay, so that I'm handling at the start only. If n is 1 and m is 1, you return 0, that there is 0 positions from which you get trapped. Okay, for the remaining, this algo is going to handle. So what I did, I started with a queue of, this is pair of int comma int. Okay, so I started with a queue of pair. So in pair, I will store the coordinates ij. Okay, so, and I have a visited array of n cross m. Okay, this is a 2D vector, vector of vector long. So I have a 2D vector of visited array from where I would mark which all cells are visited. Okay, so initially what I would do, what I put in my queue initially is, I would check if there is, if some cell is lying in the boundary and it is taking me out of the grid, then I would include it in my queue. So I move to every cell. Okay, so either this cell is in the top row. Okay, so for I equal to 0, if it is in the top row and it is taking me up, then I would move out. So if I is 0 and the value is up, then I can say that I would move out. Or if it is in the bottom row and the value is down, then I would move out. So if I is n minus 1, okay, I have indexing 0 base, so 0 to n minus 1 is my coordinates, n is not. So n minus 1 is the last. So if I is n minus 1 and the value is down, then I would say I would move out. Okay, and again for this also, if I'm at the leftmost row, that means my j is 0. So if my j is 0 and my value is left, then I move out. J is 0 and value is left, I move out. Same way, if j is m minus 1 and value is right, I move out. J is m minus 1, value is right, I move out. So for these cases, I would move out initially. So I push all of them into my queue and mark them as visited. Okay, so these are the initial, like in my multi-source BFS, these would be the initial sources. Now I run my BFS. So while queue is not empty, so I take the front of the queue is I and j and I pop the queue. So I and j is the current cell at which we are. So now what was my conditions? Whenever I am at a cell ij, I check all its adjacent cells, okay, which are present. If some adjacent is not present out of the grid, we don't check that. So all those adjacent cells which are present, if they are pointing towards it, then I would push them in my queue. So for any cell, if the cell just left to it is pointing to right, then I would push. So the left cell left to it is I minus 1 j. Okay, so if I minus 1 is greater than equal to 0, so it's not the case when I is 0, this would be out of the grid. So first I make sure that it is inside the grid. So if I minus 1 is greater than 0 and it is not already visited, okay, so obviously it should not be already visited. Otherwise, my queue would, my loop would go in an infinite loop if I'm putting the visited things again and again into my queue. So that's the basic BFS rule. So if I minus j is not already visited and I see that I minus j is equal to down. Okay, so I minus 1 was just the cell below it, okay, not left. So if this is ij, so this is a ith coordinate, I minus 1j is the cell just below it. So if the cell, okay, sorry, it's the cell above it. So if it is I, this is I minus 1. Okay, so if this is I, this is I minus 1. So if I'm at this cell, I minus 1 cell is the cell just above it. So I minus 1 j should be pointing down in order to push it into my queue. So this A of I minus 1 j should be down. If it is, then we would push I minus 1 j into our queue and mark it as visited. Okay, same way again, this was for the cell just above. For the cell just below, we would check for I plus 1, j. If it is not visited and it is pointing up, then I push it and mark it visited. For the cell just left to it, it would be j minus 1. So I comma j minus 1, j minus 1 greater than 0, and I comma j minus 1 is not visited, and it is pointing to the right. The cell just left is pointing to the right. Then I would say mark it visited, push it into the queue. And same way, j plus 1, the cell just to the right, if that is pointing left, then I mark it visited and push it into the queue. So this first thing is done. For every cell that we are visiting, all the adjacent ones, If they are pointing towards it, then we push them into my queue. Okay. If they now this one thing is done, now we also need to deal with the question marks. Okay, so if we are at a cell and there is some adjacent question mark, then we need to check whether we can push this question mark or not. Okay, so I create a check function. Okay, so what I do is I call this check function for I minus 1j, I plus 1j, I j minus 1, I j plus 1. Okay, so all the cells just adjacent to it, I check whether that cell is a question mark, and for that question mark, all the adjacent are already visited. Then only we would put that question mark into our queue. So in my check function, what I do is I would check whether that
Content
ij
you.
is already visited or not. Yeah, yes. Okay, was anybody saying something? Okay, so in my check function, what I would do is I've created a lambda function, like you can write it outside also, there is no problem. I created here so that I can access the queue and my visited. Otherwise, you can pass it by reference if you're writing it outside. So here I get all the things by reference which are present here. So you can write it outside or you can just write it here only in 4 if conditions. That would become a little bit oversized code. Okay. So what I did is I would check all the adjacent indexes, all the adjacent cells. Now, for any ij, I would check, first of all, if it is going out of the grid, then I just return back. Okay, no need to check. If I becomes less than 0, it is greater than equal to n, j less than 0 is greater than equal to m. So if it is out of the grid, then return. If it is already visited, then also return. Or if it is not question mark, then also return. So we are only checking for the question marks here. Others we have already checked, so no need to check them again. We are only checking for question marks here. So if there is some, if it is not question mark, then just return. Okay. Now, after these return statements, we are sure that there is a question mark and that grid, that cell exists. Now I check if the element just to the above it, if just above it is not visited, then I return. Okay. Basically, what I'm saying is for a question mark, if for any question mark, if I have anything, any cell to the adjacent of it which is not visited, then we would not add this question mark into our queue. Okay. We would add it only when all the cells adjacent to it are visited. So whenever we get a cell which is not visited and adjacent to it, we would return out, we would not add. So I check all the 4 adjacent cells. If I minus 1j is not visited, I return out. If ij minus 1 is not visited, I return out. If I plus 1j is not visited, I return out. If ij plus 1 is not visited, I return out. Now, if all of them were visited, then I would not find the return statement anywhere. Then I would mark ij as visited and push it into the queue. So ij was the position of my question mark. I would mark it visited and push it into my queue for the condition where all its adjacent elements were visited. Okay. I hope this extra check condition is clear to you. This was done for the question mark part. Okay. So finally, what would be my answer? My answer would be those cells which are not visited. So answer equal to 0. And for every element, if it is not visited, I do answer plus plus and print our answer. Okay.
Hello,
So
I had a question.
yes, yes,
Yeah, like for this lambda function, like for every question mark, what you are doing is, if when all the neighbors are like all the adjacent cells are visited, then you are
yeah,
checking then you are pushing it to the queue.
yeah.
And in the above condition, like in the above conditions, we are entering the if statement only if the neighboring statements are not visited. So, what is the use of pushing it to the queue?
Okay, like yes, for this, if you don't write this push also, that would be fine, because whenever a question mark is pushed to the queue, all its adjacent elements are already visited. So you may exclude this statement also. It would not affect your answer. Okay, but marking it visited was the main point, so that you in your answer you are computing that.
Okay,
Okay.
so like again, like my question was, like as I mentioned in the
Yeah.
chat, let's say for initially we do a DFS or BFS on all the source nodes, the nodes which are pointing outside the edge, outside the maze, right? Then once
Yeah.
we perform all the DFS and mark all the nodes which point to the exiting node as one and go on.
Yeah.
So after that,
Uh,
how about we iterate all the elements and for question marks,
y-
we just check if one of the adjacent element
yeah,
is
yeah.
visited.
You can do that also. You can do that also. You
Yeah,
can just
that's
exclude
correct,
this.
right?
Yeah, that would also be fine because a question mark would only be included if all the adjacents are included. So
Okay, okay.
you can just exclude this whole thing and check the question mark condition at the end after performing the BFS. That would also be fine in this problem.
Okay, yeah, that was I was confirming by my method. Yeah. Thank you.
Okay.
Thank you so much.
Okay. So I hope this approach is clear to everyone. If there is any more doubts, you can ask. If you look at its time complexity, you can see that we take the input of n into m. Okay, this base condition. Now, here we are iterating n cross m. So we are running a loop n into m times. This is an order of one if condition. So this thing is taking n into m time. Okay, this was for initial pushing the things. Now we are running this BFS. You know, the BFS takes an order of n plus like n into m, whatever is the number of nodes plus number of edges. So here the number of nodes where the number of nodes are n into m. So this would take an order of number of nodes are n into m, and the number of edges, you can say, like for every node you have four edges, like four adjacent elements. Okay, four times you are checking, and this question mark also four times is checked. So you can say 4 into n into m is the number of edges. So overall, it is 5 into n into m. So which is an order of n into m only. Okay. And this printing part is taking n into m time here. So overall, you can say that my overall time complexity would be order of n into m only. Okay. Like 1 time, 2 time, and 5, 6 times you are doing n into m. So which is as good as an order of n into m. So I hope this problem is clear to you. Can we move to the next problem now? Okay, like Akshar was asking question that you're completely stuck on graphs. So yeah, it would be recommended to like study more graph and practice some graph problems. Like BFS, DFS is the most basic part of graphs. So I would recommend that. So if you have chosen a level 3 of TLE Eliminators course, yeah, definitely. I think, okay, I think maybe graph is in the level 4. So you can study it maybe after that in the level 4 or whatever. But for graphs, okay, that graph concept is needed. The practice is needed for BFS and DFS. So yeah. Okay, so let's move to the problem D now. Okay, so here we are given that he's constructing n stone columns, each with base 0, 1, or 2. Okay, so basically we are given an array n consisting of values 0, 1, or 2. That's what it means. Then you can choose two columns U and V such that the difference in the number of encryptions between these columns is exactly 1, and transfer one encryption from the column in more encryptions to the other one. It is guaranteed that at least one column contains exactly one encryption. Okay, so what these lines means is whenever two columns have difference exactly one, then you can transfer an encryption from one column to other, from the greater one to the lower one. That just means you can swap the values of the two. So if you have something like in one column you have 2, and in some other column, in one column you have 1, in some other column you have 2, they differ by exactly 1. So you can reduce it by 1 and increase it by 2. That's what it means. It just means that you can swap these two values, okay, if their difference is exactly 1. Okay, so that's what it means. Now since beauty is the main pillar of hydraulic, once the columns of ascending height to avoid excessive water, plan a sequence of at most n moves to arrange the columns in non-decreasing order based on the number of encryptions. Minimize the number of moves is not required. Okay, so what you need to do is you are given an array consisting of zeros, ones, and twos only. You need to sort that array basically in less than or equal to n moves. Okay, and in so you are given. So what the problem states basically is you are given an array which is consisting of only zeros, ones, and twos only, and you need to basically sort this array in less than or equal to n moves. Okay, so you have n moves to sort this array. You don't need to minimize the number of moves. You just need to do it in less than or equal to n moves. You cannot make more than moves. And what are the moves? Okay, the moves means that you can basically swap two elements which differ by one. That's what uh, we can understand by reading these statements. Okay, as I explained you, it just means that you can swap two values, two elements which differ by exactly one. Now, if you have only 0, 1, and 2, that means what swappings can you do? You can swap a 0 and a 1. You can swap 1 and a 2. Okay, but you cannot swap a 0 and a 2 because they differ by 2. Okay, so that's what it means is you need to sort an array consisting of zeros, ones, and twos only with the allowed swaps as 0, 1 swap and 1, 2 swap. The 0, 2 swap is not allowed. So basically you sort this array with a 0, 2 swap not allowed in less than equal to n moves. That's what the question is. So how can we solve this? Okay. Now your n is 2e5, so you need to do it in order of n only. So how do you decide the swaps so that you do it in less than n swaps? Okay, like you can always do it in more number of swaps. Okay, what you can do is you have some array. Okay, let's say some array you have. Okay, finally, what would be a sorted array? Your sorted array would consist of some zeros. Okay, let's say there were 3 zeros, 2 ones, and 2 twos. Okay, this would be your sorted array. This is where you need to reach. Okay, so from this you need to reach here. For this you can make swaps. Okay, now maybe okay, so for sorting, like you if you apply any sorting algorithm, let's say you are doing a bubble sort algorithm, what it does, it like starts from one place and does some swaps. So the maximum number of swaps goes order of n square if you remember for a bubble sort or an insertion sort, those normal sorting techniques. And for a maybe some merge sort and all, you can do it in n log n. Okay, again from there it's not based on swapping. Okay, for those sorting techniques which are based on swapping, that only you need to consider. So there you can see that you need to do in less than equal to n operations. So general some sorting technique won't be very effective. It may include more than n. And again, you also have the restriction that you cannot swap 0 and 2. So how do you do it in n moves only? The main thing is the elements are limited. You only have 0, 1, and 2. You don't have all the things. Okay, all the numbers. There can be only three possibilities of numbers: zeros, ones, and twos. Okay, so what in your sorted array, finally, what you can say that what would be your final sorted array is number of zeros that you have, that many times you would have 0, number of ones that you have, that many times 1, and then the number of twos that you have, that many times 2s. That would be your final array. Now, okay, let's suppose now once you have computed the final array, one technique was just compare these two arrays. Okay, just sort it, like make a copy and sort that. Okay, now you need to convert this array into this. So how can you do? When you have a 0 and 0, okay, no need to change anything. Let it be at its place. Now, when you have 1 and a 0, you need to bring a 0 here. For that, you would, but you have a 1. So you would search for some 0, let's say, and swap it with it. Okay. So what you can do, whenever you have a 1, search for a 0 and swap it with that. Okay. So that way, if you perform that, okay, this place is okay. Now again you have a 0 and you have a 1 here, so search for some other one, search for some other 0 and swap it with that. Okay, so let's say I swapped it with this. Okay, then I have a 1 and here we have a 2. Okay, so I need a 1 here and there is 2 present. So search for some 1, swap it with it. Okay, it becomes 1, it becomes 2. Now again we have 1 and we need a 1 and there is 2. So search for some 1, swap with it. Okay, so this way for every place we are just doing one swapping and bringing the element to it. So in this way we can do in n swapping, but the problem in this is if you have something, let's see. Okay, here if you have swapping of a 0 and 2, that's where the problem is. You can swap 0 with 1, you can swap 1 with 2, but you cannot swap a 0 with a 2. Okay, so here 0 0 were there, no problem. Now for this 0 you need a 2, there is a 2, you need a 0 here. So in this situation when there is a 2 you need a 0, so you would have to swap like this, but you cannot perform this swapping of 0 and 2. So how can you alternatively do this? If you are not allowed to swap 0 and 2, just making use, and it's also mentioned in the problem, one more thing, that uh, it is guaranteed that at least one column contains exactly one encryption. So it is guaranteed that at least one value is 1 in this array. It's not like all the values are 0 and 2. Okay, so it is given to you that at least one value exists, which is a 1. So when you need to swap a 0 and a 2, you can utilize that 1 because through 1 you can swap anything. So you can use a 1 to swap 0 and 2. What you can do is you have a 2 here, you have a what you need a 0 here. Okay, so basically you need to swap this 0 and a 2. So what you can do is swap this 2 with 1. Okay, you got a 2 here, a 1 here. Now swap this 1 with 0. You got a 0 here, a 1 here. Okay. And this way you got a 0 here, and then this 2 can be swapped with 1 to get a 2 and 1. So basically, if you want to swap 0 and 2, you can perform cyclic swaps in that to make it like this. So in first swap, okay, so whenever you want to, at some index I, you have 0, at some index j, you have 2, at some index k, you have 1. What you can do is, in order to swap I and j, you can swap I and k first. Okay, so when you swap I and k, it becomes 1, it becomes 0. Okay, so this swapping is done. Then swap j and k. Okay, so sorry, I and j, you cannot swap 0 and 2. So swap I and j. So when this swapping is done, it becomes 2, it becomes 1. Now swap j and k. Okay, so that way you do these cyclic swaps. You can see that you wanted to swap 0 and 2, they are swapped. It becomes 2 and 0 and 1 is at this place. So in order to swap a 0 and a 2, you can perform these 3 swaps to swap 0 and 2 using a 1. So, but the problem is if there are many 0 2 combos and we are using 3 swaps, okay, that may exceed the limit that you need to make sure that it should be less than equal to n swaps. Okay, so how can you make sure that limit is okay? So what I did is, okay, so this was a little, okay, I won't say that I have a complete 100% proof to that. It was a more intuitive kind of approach. So I'll give you a rough proof why it works, but let's tell you the approach. That what I'm doing here is, if you look at the array, whatever you have, let's say some random 0 ones you have. Finally, what you would have in your sorted array, there would be some zeros, okay? Then there would be some ones, okay? And then there would be some twos, okay? So this would be the pattern for your final array. So what you can do is, the problem was with the swaps of 0 and 2 only. So what I'm telling is first try to make all these positions as zeros. Okay. So in your initial array up till here, whatever positions are already zero, they are okay. No need to change them. Only for the positions where you have one or two, you need to bring a zero in. Okay. So if let's say here there are four zeros, it means in your original array, let's say some zeros were there and some zeros were towards this right side. You need to bring them here. Okay, that's what you need to do. So first what we would do, first we would try to complete these zeros. Okay, first we would try, if you have x number of zeros, so first for the first x indices, all those non-zeros values, replace them with zero. That's what you would try first. So if you have a 1, directly replace with a 0. So which 0 would we choose? Okay, so you have a 0 here also. So what I'm doing is I'm trying to choose a 0. So I'm running like a two-pointer approach. One is trying to make them all of them 0 and one pointer is running from the end. Okay, so the first 0, the first place where there is no 0, that would be replaced by the last available 0. So the first where there is no 0, that would be replaced like this. So if it is a 1, there is no problem. Directly replace it with a, directly swap it with the last 0. Now my last 0 is here. Okay, if there is a 2, what I would do is for a 1, only one swap was needed, no problem. Now for a 2, uh, we would search for the last one that we have in our array. Okay, let's say we have a 1 somewhere here. Okay, so in order to get a 0 here, you need to utilize a 1 because you cannot directly swap 2 with a 0. So basically, you need to swap these positions. So we will utilize the last one to swap them. Okay, so why I'm using last one only, not the first one, that maybe ahead you would understand. So what I'm doing is for this two, the last one that is available in the array, I would use that and swap these two first. So this two and this one, they are swapped. Okay, so we have a 1 here and a 2 here. Okay, now I need to bring a 0. Now, once I have 0, I can swap with the last 0. So I got a 0 here and a 1. So I'll perform these two swaps. I make sure it's a 0 here. Now, the third swap would be to swap these two to get a 2 here, but no need of that. Why to? Because when we would reach that position, then we would decide that we need a 1 there or 2 there. Okay, so no need to do this swapping. We would only do two swappings. This 2 swap with the 1 and then this 1 swap with the 0. In these two swappings, we would get a 0 here. Okay, so after two swappings, we got a 0. After that, we move to the next index. It is already 0. So in this way, if we have x number of zeros, then we would be able to bring all zeros in. For twos, we would use two swaps. For ones, we would use one swaps. So for if the number of zeros are x, then in maximum, in less than or equal to 2x number of swaps, we are able to make sure that this is fine. All like initial x values are having the zeros. So the positions of zeros are done in 2x number of operations. Now for the remaining positions, what you can do, how many operations would be needed? Okay, so for the remaining positions, we would have some, let's say some 1 here and okay, so for the remaining positions, we would have some ones and some twos. So what you need to swap, you can easily swap 1 and 2 with each other. There is no 0, so there is no 0 to swap. So whenever here you have 1, 1, that is fine. Okay, so till here you have, so when you need a 1 and there is a 2, just swap it. So for this at max, whatever is the length of it, that many swaps would be needed, or less than that swaps only would be needed. So like in this location, how many swaps would be needed is when you have a 2, 2 and 1, 1, 1. That would be the worst case when you would have to swap 1, 2, 3. Three swaps would be needed. So here you can say if this length is y, let's suppose. So if length of this was x and length of this is y, so this thing would take at max y by 2 swaps. Okay, so at max there would be y positions which are dislocated, and in every swap you are swapping a 1 and 2, and two locations get fulfilled. So you can see that uh, number of operations done would be maximum 2x plus y by 2. Okay, and you know x plus y is n here. So the total, like this is x, I'm telling this is y. So total x plus y is total n indices are there. So in the worst case, what would happen is you have to do 2x swaps, okay, and y plus 2. Like now you would say that if this x is n by 2, then 2x would have like n number of operations, and then this y by 2 would have some extra operations, so that may exceed n. But I'll tell you, and I'll, but this would not exceed n. That's what I want to tell is I can give you a rough proof that why this thing was not exceed n is, if you think of the worst case, what can happen? Okay, when do we have 2x? Is when there are no zeros and all of them at initial positions are 2. Okay, that would be the worst case. Or if you have like, if this x is more than n by 2, the first thing is, if this x is, let's say, more than n by 2, okay, so you have many number of zeros, okay, and some ones and twos. Okay, let's say n was 6 and we have four number of zeros. Now for sure, if these four zeros are you cannot distribute these four zeros in two places, so at least there would be like two zeros which are already there. For them we don't need a swap. So at max it would be n by 2 only. So like this 2x, or you can say that it's not 2x but it's minimum of 2x comma n by 2 only. Okay, this upper bound, I hope it is clear to you that the like n by 2 into 2. Okay, so it won't exceed n. Then this upper bound is clear to you, I hope, because if there are more than n by 2 number of zeros, then some of the zeros would be present already here. For them, you don't won't need a swap. Only for the zeros which are not present here, for them you would need a swap. Okay, so what is the worst case? Worst case is you have all the initial n by 2 positions, they are occupied by 2s only. Okay, and then you have now, would this worst case happen? That's the first thing. Okay, the worst case would be like for n equal to 6, you have all the first three places as 2, so for them you would need two swaps. But again, you don't have a 1 here, so this is not a valid array. Okay, so let's say you have one more 1 here, so this would be a valid array now. Okay, so the worst case can happen in, if like just less than n by 2. If n is 7, then these three places are 0 and all of these places are 2. Okay, for them you would need a swap with a 1. Now even in this worst case, like this is for n equal to 7, if I'm imagining, then here you would need, for each 2 you would need two swaps. Okay, so plus 2 plus 2 plus 2, so a total of 6 swaps are already done. But if you look after these 6 swaps are already done, then in the final positioning, what you would have, you would have some twos and ones. So what is the worst case is, okay, so either after making the swaps you would already have 1 2 2 2, then ahead you won't need a swap, or maybe you have you don't have 1 2 2 but you have some 2 and 1. Okay, then you would need one swap for that one. Okay, but you can see that whatever you do for these positions, at max one swap would be needed to complete it. So if you use 6 swaps here, then in one swap you can do this. Now, what I'm doing is, what, like this was for one of the worst case, like if you think there is some n by 3 positions which are filled with 0, then in 2n by 3 operations would be utilized there. But for the remaining 2n by 3 places, again, at max, uh, you know, half of these operations are required. So n by 3 operations you can do. So if you like think intuitively or like that, more than n operations would never be required, because the array would be such it cannot happen all the positions are like all these initial positions are not aligned to 0, and then even after swapping all these are not aligned, because if those swappings are done, some of them would get aligned. And why I'm doing with the end, maybe doing from the starting 0 and starting 1 may also be fine, but I'm doing from the end so that I get more twos in the end. Okay, I think maybe doing with starting may take more than an operation somewhere, but by doing from the end, if I'm replacing the last 0 with 2, then I'm trying to push this 2 more towards the end, so that after these zeros are done in this final array, I require less number of operations. So that's why I swap it. I can swap with any of the 0. Okay. So when I need a 0 here, I can swap with any of the 0, but I'm swapping with the last 0. And for a 2, I'm swapping with the last 1 and the last 0 that I'm using. Okay. So I hope the approach is somewhat clear. I cannot give a complete proof that maybe in the tutorial it may be given, or if they have solved in the same way. I have not seen the editorial yet, but I got this feeling during the contest that this may work. So I just tried it and it got accepted. So uh, I hope it is somewhat clear to you, the approach. Okay, so we'll look at the code now. So basically what I'm doing here is, if I tell you again, is I'm uh, looking at the first array. Now to implement it, what I would do, I would create a copy of the array and sort it so that I know at what position I require what. Now from that, I would start from the start. Okay, like, or this sorting is actually not required. What I'm doing is I just need to fill up all the I need to make all the zeros come towards the start. So I run a 2-pointer approach. I start from the left end. I need to make sure whenever I'm moving, all everything behind is 0. Okay, initially I need to make sure that everything is 0. Okay, so first, if I am a 0, okay. Next, if I don't have a 0, then I pick up the last one that I have, swap it with that. Okay, next, if I don't have a 0 and there is 2, then I pick up the last one that I have, swap it with that, and the last 0 that I have, swap it with that. Okay, so the last 0 is maintained by a right pointer. So this left pointer is moving ahead, making all of them 0, and right pointer is moving to all the zeros that are available that need to get swapped. Okay, and the last one is maintained through a right through in a set. I'm just storing all the positions where there is a 1, and whenever I do swappings, the set is updated. So in login time, I'm updating the set to get the last position of the one that I have. Okay, maybe taking the last was not required. It may get accepted even without that, but I don't know. I just tried the last ones, so to maximize my chances of less number of operations being used at the after these zeros are done. So the first part is getting all the zeros, and in the next part I would just start a pointer from here and a pointer from here. If there is a 2, there is a 1, move ahead, move ahead. Whenever I find a 2 and a 1, interchange them, swap them. Okay, so that way a 2-pointer approach like that would solve the second part. So let's move at the code and understand. Okay, so first I take the input. Okay, an array of size n. Okay, then what I do is I initialize a set to store the initial positions of all the ones. Okay, so whenever I get a 1, I insert that into my set. Okay, so I inserted all the positions of 1. Okay, I am inserting I into the set, all the positions where there is a 1 into my set. Now I initialize 2 pointers, L as 1, R as n. Okay, so I'll move in the 2-pointer approach. So while L is less than R, I'll check if AL is 0, then I do L plus plus. So whenever I get a 0, I move ahead. No problem, no need to change anything. Okay, so I do a continue. When I don't get a 0, I need to replace that with a 0. So in R, I would move my R to the left to find the first 0 from the right, which is the first 0 from the right, which is available. So until R is greater than L and the value is not 0, I do R minus minus, so that whenever I reach a value having 0, I break out. okay, or this loop condition becomes false and I get out. Or if this R becomes equal to L, then also I would get out. Okay. So if this R becomes less than equal to L, I'll just break out of the loop. Then that towards the right of L, I don't have any zeros. That means all the zeros are done. All the zeros are stacked to the left. My initial part is done. Okay. Now, when this AL is 1, I need to swap AL and AR. Okay. So at AR, I have a 0, and at AL, I have a non-zero element. So I swap AL and AR to get a 0 at L and 1 at R. So in my answer, I initialize, for storing the answer, I initialize a vector of pair. So this is a vector of pair of long long. So in that, I push back just whatever swapping I am doing. So when I'm swapping LNR, I push back LNR so that I also need to print all the swappings that I'm doing in my final answer. So for that, I'm storing them. Now, for the position of 1, now since 1 was at position L, okay, so 1 was at position L, now it is swapped to position R. So I would erase L from my pos set and I would insert R into my set. Okay, so the updated positions of where 1 is present is now updated. Okay, else part, what I do is when AL is 2, then I take the position of 1, the highest position of 1 that I have. Okay, in J, I get the highest position of 1 that I have. And what I did here, what I was doing, okay, when I have a 2, okay, whichever is the highest position of 1 that I have, I swap that 2 with 1. Okay, so if this is my index L. Okay, the last available 0 is at index R, and this index J represents the last one. So first L and J would be swapped. Okay, so that I have a 1 here and a 2 here. And then this 1 would be swapped with the 0 with position R to get a 0 here and a 1 here. So first LJ swap would be done. And then, okay, first LJ would be swapped, L and J, and then L and R are swapped. Okay, so then swap AL and AR. Okay, in answer also I push back LJ and LR. The operations that I'm performing, I'm storing them in my answer vector. And if you look at the position of 1 after this swapping, 1 was here, now 1 is moved to here. So 1 was at J, now 1 is at R. So I erase J and I insert R. Okay, so I hope this is clear. Now we have a 0 at AL. So I do L plus plus to look at the next L. Okay, so this way, after this while loop is done, we have segregated all the zeros at the start. That part is done. Now the second part would be to just evaluate this. So I start, my L is now here. Okay, so I keep this L now and update my R to N. Okay, so R would be updated to N. Okay, then again I run a 2 pointer from here to here. Whenever I have a 2, 1, I swap them. Okay, so if AL is 1, that's fine, L plus plus and continue. Okay, so when AL is not 1, it is a 2, then I try to get a 1 from the end. Okay, so I do till the time AR is 2, I do R minus minus. So whenever, if R becomes less than L while doing this, I break out that it is done. All the ones are to the left of 2. Okay, else I would swap AL and AR, push into my answer and do N plus plus. I hope this part is also clear to you. Okay, finally, I would print the size of my answer and each element of my answer space separated and in the next line. Okay, so I hope this code is also clear and logic is also clear to you. If there is any doubt, you can please ask. If you analyze its time complexity, like this is the input part, which is taking like n-sized array, then this inserting into the set takes log n time. Okay, log of the size of set, so at max n elements, so log n time. And this is done n times. So overall, this thing would take n log n time. Okay, now I initialize this answer. Now in this while loop at max, this is like a 2 pointer approach. So at max this L and R, okay, like they are running at max n times. Okay, and this swap and all are order of 1 operation. This erase and all is log n operation. Erase and insert take log n operation. Again, this erase and insert also take log n time. Okay, so overall this log n time every iteration is taking, and this overall, like these two while loops combined are running at max n times. So this I can say is taking n log n time only. Okay, this whole loop. Okay, then again, this is again a two pointer from L to R. And here we are doing nothing, just swap, no log n operation also. So this is taking n time at max. Okay, so overall time complexity I can write is n log n here and n log n here. Okay, so this n is less. So overall, I can say it is n log n. Okay, and the space complexity would also be like I'm using a set of size n and a vector of size n, so everything is order of n only. Okay, so is there any doubt in the logic or in the code? You can ask. What is the maximum rating one can achieve if he has taken a level 3 course? I think according to level 3 course, it is for somewhat you can solve problem C's. Okay, so maybe in sometimes you have graphs in problem C, but most of the time you don't have graph trees, and DP you have sometimes. So I think 1500, 1600 you can achieve, but that rating is not dependent just on the topics. So like it's more about how much practice you do, how much contest you do regularly. If you look at the starting problems, the graphs are like very rare. Like in this contest, you had a graph in problem C, but graphs are mostly in DE or after that also. It's more of the constructive things that you need to practice more initially, okay, before moving to graphs and all. So I think that is more important. It's more about the practice, not the topics that much. So I had given 25 contests. Okay, like this thing happens. Maybe for everyone, the pace is a little different. But the more practice you do, the more regular you are, you would improve only whatever you are there. And sometimes the rate in rating, you don't see the improvement. After some time, you may see the improvement. But if you do practice regularly and all, then you are improving. That's the thing. I just don't see rating too much. Rating does not matter that much. Like it's only for giving you a good feel of like when your rating increases, you get a good feel. That's the more important thing. Okay. Okay. I hope if you have any doubts regarding this problem, tell me, or maybe we can end the recording now. Then you can ask the general doubts. Okay. I think it's clear to you. So thank you very much for watching. Goodbye, everyone.